Good afternoon and welcome to our presentation on FaceCraft.
I'm Timoteo, and my team members are Ethan and Will. For this project, I helped with the development environment, clip integration, and latent space manipulation.
For this project, I was a machine learning engineer. I helped with the front end development on Hugging Face. I helped with training and debugging the model, and I worked on Docker containerization.
And for this project, I was also a machine learning engineer. I worked on the back end, building the StyleGAN2 from a research paper and the StyleGAN-T network from a research paper. I was also responsible for training and debugging the models.
This presentation will be about our research and development journey into the fascinating world of generative AI, focusing specifically on realistic image generation using generative adversarial networks, or GANs for short. We chose to explore the realm of generative AI to gain a deeper understanding of neural networks, data processing, and the technical challenges associated with AI. During this presentation, we will explain what a GAN is and share details about our development environment. We will walk you through the process of training a GAN, explaining why we selected a specific GAN for our research, and explain the inner workings of these networks. We will finally discuss the challenges we encountered and how we overcame them, highlighting both our setbacks and successes.
A GAN, or generative adversarial network, is a type of AI model that consists of two neural networks, the generator and the discriminator. These two networks work against each other in a competitive setting. The generator's job is to create synthetic data, such as images or anything else, by learning from a set of real data. Its aim is to produce outputs that are so realistic that it can't be distinguished from actual data. And that's where the discriminator comes in. Its role is to evaluate the generated data and try to tell it apart from the real data. As they compete, the generator gets better at creating realistic data, while the discriminator becomes more skilled at spotting fake data. This ongoing competition pushes both networks to improve, ultimately leading to the generation of highly realistic synthetic data.
Why we chose StyleGAN2 over others. When training a GAN network, it's essential to have enough physical space within the graphics card to accommodate the network. Different types of GANs have varying GPU memory requirements. For instance, the StyleGAN2 network works well with 8GB memory on your laptop GPU. However, we found that StyleGAN-T and StyleGAN-ADA both require significantly more memory, to the extent that they are unable to train correctly with our current setup, either personal or work. This issue became evident after we trained a StyleGAN-T network for a few hundred hours, leading to us choosing StyleGAN-2 over its compatibility with our available resources.
Training a GAN is an iterative process where two neural networks, a generator and discriminator, learn together in a competitive setup. It starts with feeding random noise into the generator, which creates synthetic data. The data is then mixed with real data and fed into the discriminator, which tries to tell the difference between the real data and the synthetic data. Based on its successes, two loss functions are calculated, one for the generator and one for the discriminator. The generator's loss shows how well it fooled the discriminator, aiming to reduce this loss so the generator can make more realistic data. The discriminator's loss shows how accurately it identifies real and fake data, aiming to increase this loss to improve its detection skills. This process is repeated over many iterations, with the generator getting better at creating realistic data and the discriminator getting better at spotting fakes. Over time, this back and forth competition leads to the generator producing highly realistic synthetic data.
The fields of artificial intelligence and machine learning are rapidly growing and being widely adopted across many industries, with GANs leading the way in innovation. Our product, which uses GAN technology, is aimed at key sectors such as entertainment and media, healthcare, e-commerce, and retail, and fashion and design. In these industries, GANs are transforming processes by enabling realistic image creation, improving medical imaging, offering virtual try-on experiences, and streamlining design tasks. Our goal is to harness GAN technology to develop groundbreaking features for these applications. Training GAN networks, especially complex ones like StyleGAN-T and StyleGAN-ADA, requires significant resources and time. Each iteration of a production-ready model can take around 100 hours to train, making rapid prototyping difficult. Despite these challenges, we successfully developed a minimum viable product that demonstrates the potential and impact of GAN technology. This MVP underscores the need for scalable solutions and optimization techniques. With more time and resources, our product can evolve into a fully ready solution, driving advancements and opening new possibilities in our target markets.
Features of our network. Generating random images. Our network can create completely new and unique images from a random latent space.
Generating from prompt. Users can input text descriptions and the network will generate images that match the given prompts, providing customized and relevant visual content. This is done by using clip for text encoding that creates a latent space for the generated image.
Generating from an image. By using an existing image as reference, the network can produce variations or enhancements, potentially making it useful for tasks like photo editing and transformation.
Applying filters. Our model applies various filters to modified image appearances using CV2.
Background removal. This feature enables the network to separate the main subject from the background by using head segmentation. It masks the head, then removes the unmasked pixels, which are the background.
And finally, image manipulation. This feature allows the user to manipulate the generated image's latent space. By moving the slider, the image will transform and augment by the new latent space it receives.
What went right for our research? Hugging Face. We utilize Hugging Face's platform for its resources that significantly streamlined our development process, providing robust support for integrating advanced AI models. StyleGAN 2. We chose StyleGAN 2 because of its effective performance, as it offered a good balance over resource requirements, allowing us to create high-quality images without overwhelming our hardware. Clip. We use Clip with text-to-image generation for manipulating the latent space by providing a pre-trained natural language processing encoder. This is what allowed our StyleGAN 2 model to generate images from a prompt. Latent space. By manipulating the latent space, we were able to augment and change features of a generated image. Filters. We applied filters by manipulating the pixels of a generated image using OpenCV. This is what created Cartoonify, Pencil Sketch, and even the watercolor effects.
The obstacles we faced. Switching from WSL to Linux. Initially, we encountered issues with WSL, as it did not work well with the Docker and training the network. To address this, we switched to Pop! OS on Linux, which provided a more stable and efficient environment for our project. StyleGAN T. We faced significant challenges with StyleGAN T due to its high resource demands, which exceeded our hardware capabilities and led to training inefficiencies. Training going back due to technical limitations. During training, we experienced issues where the outputs would go black, indicating potential problems with memory limitations and model complexity, which hindered our progress.
Going forward, what we would do differently. We plan to do all future AI projects in Pop! OS, as it proved to be more stable for the machine learning pipeline compared to when we're working with WSL. Linux offers robust solutions in a very lightweight package, which is very crucial when every bit of memory is accounted for and needed. I would also consider conducting the main training of the network on a cloud-hosted service like Amazon Web Services or Google, depending on our budget. This shift is due to hardware limitations and the significant electricity requirements involved in training a network on a home machine. Using cloud services would provide greater scalability and efficiency for future projects.
Thank you for listening to our presentation. This was FaceCraft, and we hope to facilitate more research in the future.